Hi guys, this video is on motivation behind the study of rings. In other words, its purpose. Why study rings? If you look into our mathematics, the algebra it generally consists of two operations. Like in the case of integers, there are two operations, addition and multiplication, and these two operations they always come together. They rarely come separately. So because of this, because our algebra consists of two operations, the equations to be solved, the equations in our hand, they also consist of two operations. Take an example of this equation, x squared plus 2x plus 1 equals to 0. It involves two operations. And the type of the equations we'll be dealing with are also these type of equations. And ring is the abstraction of such a case. It is the abstraction of our algebra with two binary operations. Our first topic is polynomials. We give a different viewpoint of polynomials, different but very important viewpoint. It is key that you understand this viewpoint. First, we call x indeterminate then variable. Let x be a polynomial of zx, then x is not equals to 1 or any element of z. The nature of x is not determined, so we call x indeterminate. Second, we never write such things as x squared minus 4 equals to 0 simply because x squared minus 4 is not the zero polynomial. It's not the zero polynomial. So we do not solve equations because we do not write such things. We find the zero of polynomial. 2 squared minus 4 equals to 0. So 0 of x squared minus 4 is 2. But note that x is not equals to 2. We do not write x equals to 2. The value of x is not 2 because x is indeterminate. Only the 0 of the polynomial x squared minus 4 is 2. Our second topic is ring of polynomials. The set Rx is the set of all polynomials in an indeterminate x with coefficients in ring R. The set Rx forms a ring under polynomial addition and polynomial multiplication. Further, if R is commutative, so is Rx. And if R has multiplicative identity 1, then 1 is also multiplicative identity of Rx. The proof it directly follows from the fact that R is a ring. Our third topic is the evaluation homomorphism. Let phi be a subfield of E and alpha be any element of E and x an indeterminate, then a function phi alpha from the ring of polynomials fx to the ring E such that phi alpha px equals to p of alpha for all px in fx and phi alpha a equals to a for all a in f. Then phi alpha is a homomorphism, and this homomorphism is known as the evaluation homomorphism or simply evaluation at alpha. Now I'll give an illustration of this. Q field of rational numbers, R field of real numbers. Q is subfield of R, root 2 belongs to R. Let x squared minus 2 and 2x plus 3 be two polynomials of qx. Then phi root 2 of x squared minus 2 is root 2 squared minus 2 equals to 0 and phi root 2 of 2x plus 3 equals to root 2 plus 3 from definition of phi alpha. So the evaluation of 2x plus 3 at root 2 is 2 root 2 plus 3. Evaluation of x squared minus 2 at root 2 is root 2 squared minus 2, that is 0. Now let me emphasize the importance of the evaluation homomorphism in field theory. The phi alpha, very simple homomorphism, but foundation of all our further work in field theory, it lies on phi alpha. It is that important in field theory. Finally, we can answer to the questions why study rings, fields and ideals. Now solving polynomial equations have been the oldest problem in mathematics. This new approach, it makes the connection between our old ideas and new ideas. Our old idea, solving equations, our new idea, finding zero of polynomials. This new approach, it makes connection between solving equations and finding zero of polynomials. These two ideas are the same thing. And our basic goal is to find the zero of polynomials. So why study rings, fields and ideals? To find the zero of polynomials. This is our basic goal and this is the purpose of studying ring, fields and ideals.